Good evening, ladies and gentlemen. Welcome to Lecture 7 of Topic 1 of Unit 4, Electromagnetic Flux and Electro-Motive Force, and we'll just shorten it to Flux and EMF. This video is going to be covering the main ideas of Chapters 8.1 and 8.2 of Book 2. Please complete this reading before class. Here are your learning intention and success criteria for the chapter. Please pause the video and attempt to do the KS table down there on the bottom right. Okay, so having a look here, we can see that we're learning about describing magnetic flux and using change in flux to calculate induction via this thing called electromotive force. And we need to be able to describe these things, flux, induction and force. We need to be able to calculate the change in flux and then use that to determine the force, and then describe how this force causes induction. So in terms of our knowledge, well, we need to know what flux is first. We need to know what is electromotive force. We need to know what induction is. Without these, we can't define them, and then we can't describe it. And then in terms of skills, that's weird. How do I calculate the electromotive force? And how do you calculate magnetic flux? Alright. So in class, we've used iron filings to look at the pattern of a magnetic field around different magnets, and we saw something that looks a bit like this. Now, when Faraday did his work, he called this a flux. Okay. Now, we've changed the definition because we started talking about fields, and Faraday's flux was what we would call a magnetic field, but we've kept the word and used it for something else here. And so we use this to refer to the total amount of magnetic field in a given area. Okay? If we define a standard area of 1 meter squared, the amount of magnetic field going through it would be the flux. And this is a new definition for magnetic field, okay? Because magnetic flux is the total field passing through an area, and so the field will be the amount of flux in a given area. Okay, so the Chapter 7 definition was that the magnetic field was the force on a moving charge, and so using this definition here, we have the following equation. Okay, so this is a magnetic field. Okay, so the formula. The symbol here is the symbol phi, P-H-I, and the product is BA cosine theta. Okay, now the theta here is a bit of a weird one, so let's start with the easy bits. Firstly, the phi is just flux in Webers, or properly pronounced Weber, because it's German, but we're going to say Weber. Don't forget the little b next to it. Magnetic field strength in Tesla. Okay, still B is our magnetic field strength. A is area in meters squared. That's an important one because if you're dealing with things in centimeters, convert them to meters before you calculate area, or if you're comfortable, convert centimeters squared to meters squared, that's fine. If you're dealing with really small things like millimeters, you're going to have to convert. I really recommend you convert everything into metric units of meters first, and then calculate your area. But this next one's a bit of a weird one. The angle between the field and the perpendicular vector of the area. Okay, now what this means is if we imagine an area, like this screen here is an area, the perpendicular vector is the thing that is perpendicular to the whole area, so coming out at right angles. If I move it up towards, so it's coming right up towards the camera there, and you can see it's coming out. This would not be perpendicular, it's at an angle, that's at an angle, still not perpendicular. What we mean is it's coming straight out. Okay, and so if the magnetic field comes in, okay, and the area is pointing straight up, then the angle is 0 between it. If this was twisted a little bit so that it was on its side, so instead of being flat, it was on the side a little bit, and the perpendicular vector was off to the side, then there would be an angle between it. This also means that if the angle is 90, so if my area is pointing side on, then we will have no flux through it because it is at its right angle. Here's a couple of pictures that help us visualize this. Here's the area, and here's our perpendicular vector for the area. Or in this case here we have our magnetic field going through, and it's going through perpendicular to the area as well. So here the angle would be 0 because the area is flat and basically at a right angle with the with the magnetic field. Okay, so let's have a look at a couple of examples. So our first example here, calculate the flux threading a circular loop of diameter 24 centimeters, okay, with the plane of the loop at right angles to a field strength of 5.0 millitesla. Okay. So we need to calculate, let me just load it up on my other screen. We're calculating flux. This was 8.1a. We have been told that the diameter of our loop, so let's draw our loop, the diameter equals 24 centimeters, or let's just convert it straight away, 24 times 10 to the negative 2 meters. Or you could write it as, if you're fine with it, 0.24 meters. Either of those, you're going to get the same answer. And we need, we've got a magnetic field strength. B equals 5.0 millitesla, or 5 times 10 to the negative 3 Tesla. And we are told that it is calculate with the plane loop at right angles to the field strength, so the magnetic field will just be coming through it. So I'll just draw some dots to say coming through. We could draw crosses. We don't care about the direction it's actually going here. We're not doing a vector product, but yeah, dots are easier than crosses. And we need to know, well, what's the area? Because remember, this is our formula. Phi equals BA cosine theta. Now, our theta, because it's coming at right angles, will equal 0 degrees. Okay. Remember, we're after the angle between the vector and the perpendicular area vector. So here is our shape. The perpendicular area vector would be coming out of it or going straight into it, and so the angle between the two is 0. Alright, now B is 5 times 10 to the negative 3 times, let's just leave a blank for area at the moment, and our cosine of 0. Now, this is the bit where you need to just remember some of your old geometry, because with area we've got a circle, and remember our area of a circle is equal to pi r squared. R is always going to be half the radius, pi times 0.12 squared, and if we chuck that into there, that will give us an area of 0.045. Let's stick this in, 0.045. That point a bit higher. Now we can plug that in the computer. Cosine of 0 is just equal to 1, and so we have 2.3 times 10 to the negative 4 Weber. Now, Walling doesn't introduce the cosine part of this formula at this point, but I personally don't see why we can't just start off with it, so we may as well. Alright, next one on the track. Got another example. So example 8.1b. A loop of area 1 meter squared, that's nice, we're given the area, is placed in a magnetic field strength of 4 Tesla, as shown in figure 3. Calculate the magnetic flux threading the loop when it's perpendicular makes an angle to the field of 50 and 90 degrees. So we have a couple of different things here. So the diagram is up above it. I don't believe I've included the picture. No, I haven't. It's just above on page 212 in your textbook, if you would like to take a look at that. So, 8.2a. Again, we're trying to find out flux. So, but we'll get two parts to this. So let's do this, A and B. So flux is equal to unknown. Now, we're told that the area is 1 meter. That's nice, we won't have to do much with that. We're told that the magnetic field strength is equal to 4 Tesla. And in our two situations, we have the first has an angle to the field of 50 degrees, and the second one has an angle to the field of 90 degrees. So let's just draw what that would look like. So if the field is going this way, then our area, our loop, is something like that. So if I draw the perpendicular vector, this angle here must be 50 degrees. Well, for this one here, our loop, okay, so there's our perpendicular vector. We can see here the perpendicular vector has an angle of 90 degrees with it. Okay, probably should have drawn in a different colour just to make it clearer. Now, same formula, phi equals BA cosine theta equals 4 times 1 times the cosine of 50, and we get an answer of 2.6 Webers. Now, let's just talk quickly about check steps on here. Your calculators will often be in radians for other classes. Okay? So you should make sure that you are double checking that your answer is correct or that your calculator is correct beforehand. If we think about how the cosine of something behaves, here we have 4 times 1. So the cosine of this could go anywhere from 4 down to 0. The cosine of 50 is just past the halfway point, and the halfway point is about 0.707. The cosine of 45 is about 0.707. So that means, okay, our answer should still be a little bit, because we're not at 60 yet. Cosine of 60 is 0.5. Okay, and so we should be a little bit more than a half, and we can see we're correct here. If you put 50 radians into it, you would get a very different answer. Okay, so double check and make sure that you're sort of thinking, well, is this appropriate when you're doing things with angles, because it is a silly thing to have happen where you lose marks because you haven't done a change. And having a look at the other one here, well, the same formula. Let's plug in our numbers. 4 times 1 times the cosine of 90, and the cosine of 90 is equal to 0, so our answer here will just be 0 Webers. Okay, so this is saying that because it's it's parallel, or because the area is parallel to the field, okay, or the perpendicular vector is at 90 degrees to the field, we have a situation here where it's just equal to 0. The thing is that they could have achieved the same thing with putting a sign, but there is a reason for it. It just escapes me, so we'll just have to go with it. Okay, and our last example from this set. So, yep. So here's 8C. A 25 centimeter long solenoid of diameter 5.4 centimeters with 1200 turns of wire carries a current of 1.5 amps. Determine the flux inside the solenoid, so in that empty hollow area that goes through the center of the solenoid. Now remember, we have formulas for the magnetic field strength of a solenoid, and we're going to need to use that in order to work this out. So let's flip this over. So I'm just going to draw a quick solenoid here. So we have our tube, we have our wire, now we don't know if the let's see, which direction is the current going. Doesn't actually matter because we're not caring about the direction of a flux. So I equals 1.5 amp. Let's just assume it's going this way. So if we were to use our right hand coil rule, it's going over the top, and so our field would be coming this way. We don't know our magnetic field yet. We need to work out our area. Okay, the angle in this case, well, we're dealing with a cross section, so that we're dealing with our area this way, okay, and the field is going up through the middle, so that the angle in this case will equal 0. But how do we work out the magnetic field for a solenoid? We need to use the formula. Let's see, we are told that the diameter equals 5.4 centimeters, so the radius will equal 7 centimeters, equals 2.7 times 10 to the negative 2 meters. Okay. What else do we need here from the question? We're told that the number of turns, n, equals 1200, and the length of the coil of the solenoid, is equal to 25 centimeters, equals 0.25 meters. Okay, now our magnetic field formula for a solenoid, B equals, I don't know, I'll put a tail on that, mu naught n I. Now remember, this is what you're given, okay, but this n is the ratio of n to L, so I always like to rewrite it, mu naught capital N over L I. This way we can just substitute everything in. Okay. Now mu naught is equal to 4 pi times 10 to the negative 7, isn't it? Let's just put the actual value in. 4 pi times 10. Yeah. 4 pi times 10 to the negative 7 times 1200 divided by 0.25 times a current of 1.5 amps. And we would get a total field strength of 0.0076 Tesla. Now we can take this and shove it into our flux formula. Phi equals BA cosine theta. B 0.076. Well, we need to work out our area. That's going to equal 2 pi r squared equals pi times 2.7 times 10 to the negative 2 squared. Do make sure you square the power that's on the end, okay? Otherwise you'll end up with something like, 2.7 squared is going to be equal to just a bit under 8ish, okay? You end up with 8 times 10 to the negative 2. You should end up with 8 times 10 to the negative 4. And then we're going to have multiply that by pi, which will give us 0.0023. And the cosine of the angle, cosine of 0, because it is the perpendicular vector is parallel to the field. Complicated to say. 1.7 times 10 to the negative 5 Webers. Now, that's sort of the type of question you could really expect when you're dealing with magnetic flux, because the flux formula is pretty straightforward. B times A, and if there's an angle, deal with the angle. But this allows them to check multiple things at once. So you've got your solenoid and you've got your current carrying wire, right? And so they're probably not likely to use the current carrying wire, because for any given area your field is going to be changing as you go further away from the wire. However, for a solenoid, well, that's a very obvious thing that they can do, because one of the important things about a solenoid is that the center of it, the hollow core, has a consistent magnetic field. Okay, it's not changing all the time. Alright, now let's have a look at what we can do with magnetic flux. So, we saw in previous videos, excuse me, that an electric current makes a magnetic field, and this example here uses this. Okay. Now, in the 1800s, Michael Faraday, Ampere, what was Ampere's first name? I forget. Ampere and Henry were all looking at trying to do the reverse, okay, trying to make an electric current using a magnetic field. Now, Faraday used a bar magnet, a solenoid, and an ammeter, and noticed that when the magnet moved in and out, current was generated. Okay, You did this. Magnet goes in, made a current. Magnet stop, no current. Magnet goes out, makes a current the opposite direction. And we did this class. Okay. Now this is electromagnetic induction. Okay. When a changing magnetic flux near an electrical conductor creates electromotive force or voltage. Now, because there is a current and there must be a resistance in the wire, there must be a voltage to push on the electrons, and that's what they're calling electromotive force here. Okay, so electromotive force is when charged particles are moved, causing a difference in potential that can cause currents to flow, and that's measured in volts. Now, this still happens even if there's no circuit. Okay, so if we had a straight length of metal and we moved a magnet near it, you're going to get an electromotive force happening in it. Okay? Now, EMF, electromotive force, no, it's not electromagnetic force, it's electromotive force. Through testing, several things were identified. Okay? First off, the field strength. The stronger the magnet, the more force you get. Our next is our time interval. Okay? And I've written this here as 1 over t. If we make it go faster, okay, we get more EMF. The area. Okay, so how much of an area we're using here. So for example, our solenoid, a wider solenoid, bigger area. Okay. The angle between the field and the perpendicular of the area, like we just saw with flux. It's the exact same idea. Okay. And then finally, the number of turns for a solenoid. And possibly annoyingly for you guys, this gives 2 formula for the book, in your formula book. Okay, so let's have a look at those. Here are your 2 EMF formula. So, we can see here EMF for both. On this one here, the negative will be important. We'll deal with that in a little bit later on. We'll just keep it in track. Here we have changing of B or A, and A perpendicular in this case, remember, multiplied by N over the time taken, or, because remember that B times perpendicular area equals flux, they've also rewritten it in this form. So they've given you both of these forms. Okay? But it has to be about the change in the flux. That's really important. If the flux doesn't change, nothing happens. You still need to work out, if we were to expand this out properly, you would still have the B initial times the area, so yeah, B initial times the area initial, sorry, B final times the area final, take away the B initial times the area initial, but a lot of the times they don't write it like that. So we just have to be really careful with the formula, and we'll do some practice with these ones. Now, Walding does make some of his own formula in the textbook to look at, well, what about when you have a change of field? What about if you have a change of area? Or what if you have a change in angle? Okay, and you might be going, wait, I don't see angle anywhere on here. Boom, there it is. I know, very undramatic. Okay, this one is not given to you, which is really sucky in my opinion. So, but the thing is, phi equaling BA cosine theta is given to you in your formula booklet. So keep that in mind, that phi will change in response to a changing of angle. Okay, so he provides a few different formula. I wouldn't recommend you try to memorize them. Okay, I would recommend that you calculate the change and then substitute, because here's the thing, if you think, well, what's the change in B, but B hasn't changed in the question, you end up with a 0 slapped into there, and then anything times 0 is just 0, so you might go, there's no electromotive force. But if the area changes and the magnetic field doesn't change, you get you do get an electromotive force. Okay? If both of them change, you get a force. That's cool. Okay, we can deal with that. Okay? But if one doesn't change, you've just got to be aware of it for the formula. Okay, and we'll see. I'll show you how to write that out. So let's have a look at our first example. We're going to do the same scenario for each of these in terms of the same numbers, but we're going to change different things each time. So here's our first example. A magnetic field strength of 4 millitesla, threads passing through a loop of area 1.5 meters squared at right angles to the plane. The field strength suddenly was reduced to 1.1 millitesla in 0.5 seconds. So we're going to calculate change of flux and then calculate the EMF. There's no light, there it is. Let me load this up on my screen so that, whoops, there it is. Okay, there's the example. So, I'm going to write out the formula. EMF equals negative N delta B A cos theta over change in time. So this formula is going to be the thing we keep referring back to each time. So 8.2a. So we are told that our initial equals 4 millitesla, 4 times 10 to the negative 3 Tesla, and our final equals 1 times 10 to the negative 3 Tesla. Our area is just 1.5 meters squared, and our angle, well, the picture that has underneath it is, we're told right angles to the plane. So remember, if the field is right angles to the plane, then it is parallel to the perpendicular. I will just draw that out quickly. Here is our plane area, but here is our perpendicular vector. Here is our magnetic field, so the magnetic field is perpendicular to the plane. It's parallel to the area vector, and so angle equals 0. And we're told that the time it takes to do this is 0.5 seconds. Okay. Now, it asks us to work out the change in flux. Remember, that's just the top of our scenario here. So let's do it in a couple of different ways. So change in flux equals flux final, take away flux initial. Remember, this is our definition for a change. So that's going to be our B A cos theta, just put brackets around that, final, take away B A cos theta initial. Now, A and cos theta are still the same, it's only B that's different. So let's do a little bit of factorising here. A cos theta times BF, take away BI. And we have all these. We have A, it's provided. We have theta, we've determined that from reading the question. We have our two differences. So equals 1.5 times cosine of 0, which will just be equal to 1, times 1 times 10 to the negative 3, take away 4 times 10 to the negative 3. Well, that's just going to be 3 times 10 to the negative 3. Sorry, negative 3 times 10 to the negative 3, and negative 3 times 1.5 should equal negative 4.5 times 10 to the negative 3 Weber. Okay, so there's part A. And part B of this, the EMF, remember, is negative N phi over T. Well, negative N, there's only one loop, so that's just negative 1 times negative 4.5 times 10 to the negative 3, and it happens in half a second, so that would equal 9 times 10 to the negative 3 volts. Okay, we're back to volts again. Now, let's do this using just this formula here. So if we put it all into this one form to work out this last bit, because if you were working out the change in flux, you would have to go, well, what's the flux initial, flux minus? You could just substitute the numbers into both of these if that would make you feel better, but a little bit of factorising can make it a bit quicker for you to do the math on your calculator. So if we chuck it all into the EMF, we get that EMF equals negative 1 times, so we've got our delta BA cos theta. Okay, so really what this is saying here is this here, the final of this, take away the initial of this. Okay, one way of thinking about it is, well, let's just delta the only thing that's changing. Okay, A is not changing, theta is not changing, but B is changing. Okay. And delta B, we can see is just going to be this, take this, 1 times 10 to the negative 3, take away 4 times 10 to the negative 3, equals negative 3 times 10 to the negative 3, all divided by our delta t, which we have over here. And so now we can substitute and get negative 1 times 1.5 times the cosine of 0 times negative 3 times 10 to the negative 3, all divided by 0.5, and then we have our answer of 9 millivolts, or 9 times 10 to the negative 3 volts. Now, you might go, well, wait, there's a negative out the front here. What if we'd had a positive number for our delta instead? What would that do? So remember, positive voltage means we have conventional current, okay, going from positive to negative along our the direction that all the rules that we've been playing with. So, if we know that we haven't dealt with direction yet on this, we'll get to that in our next video. But we go, okay, well, whatever the normal right-hand rules that we've been using work it out as, that would be our direction. If it had been a negative, the direction is just the opposite. That's all that the voltage is doing there. Okay. All right, let's have a look at 8.2b. I need to grab a new piece of paper as well. So that was change of field. Let's have a look at the next one. Same setup. Okay, field is 40 millitesla, area is 1.5 meters squared, but the loop is now turning. Okay, determine the EMF generating the loop. Okay, now we're skipping the working out the flux part, we're just going straight to the EMF. Okay, so let's get this done. 8.2 B. So we know that our B equals 4 millitesla, 4 times 10 to the negative 3. Our area equals 1.5 meters, and our little t equals 0.1 seconds. Okay, we're dealing with one loop, so n equals 1. Now, our initial angle is equal to 0 because our picture, let's see if I can draw this quickly for us. Our picture is our vector, our area vector, and the field is going this way. So they are parallel, and so the angle is 0. But now, okay, let's see if I can do this. There's our magnetic field, but now, okay, our perpendicular vector is going off at an angle, and we're told that the angle is 20 degrees. Yes, 20 degrees. Now, one thing you've got to be really careful here. You can't just go, oh, you change of angle 20, chuck it in, and you're done, because you wouldn't actually be working out any change. It's the change of the cosine. So let's write the formula. EMF equals negative n delta BA cosine theta. See how the cosine is after the delta? So it's the change in the cosine of the angle, not just the change of the angle, over delta t. Negative n. Now, B, not changing. A, not changing. But cosine, the angle is. So cosine final, take away, cosine initial, all over delta t. Okay, so you've got to make sure that you do that appropriately. What you could do is work out the flux and go, okay, BA cosine of 0 and BA cosine of 20, and then work out the difference that way. Okay, remember, final take away initial, not initial take away final, and then multiply the rest. That would work without a problem. Okay, and that would be how you'd find out the change in the flux first. So you're just doing BA cosine final, take away BA cosine initial. That would give you the change in flux. Remember, flux is this, and that's why I don't like the name for it, because to me flux means movement, but flux is just a static thing. It's the amount of field going through the area, and you've got to take the angle. So you can work out the change without a problem. And if you were being asked to work out the EMF, there's nothing stopping you from working out the flux, the change in flux first, and then substituting it into the EMF equals n delta phi over delta t formula. that's perfectly fine. Don't feel that you have to do it to jump straight to this step. So let's show our numbers in. -1 times b, 4 times 10 to the -3 times 1.5 times the cosine of 20, take the cosine of 0, all over 0.1, and that gives us an answer of 3.6 times 10 to the -3 volts, or 3.6 millivolts. Okay. And our last one is dealing with a change of area. Let's bring up that question. Oh, I did have the picture in here, I didn't even notice it. Okay, so didn't have to use my horrible drawing. And our last example, same setup. The magnetic field is 4 millitesla, passes through 1.5 meters squared at right angles. The loop shrinks to 0.6 meters in 0.1 seconds. Calculate the EMF. Did I put the... No, I didn't put the picture on this one. This one should be pretty easy to visualize. We're just making the area smaller. Calculate the EMF and the loop. I think I have enough room here. 8.2c. B equals 4 times 10 to the -3. A initial 1.5 meters squared. A final equals 0.6 meters squared. Theta will equal 0. We're dealing with perpendicular again, and delta t equals 0.1 seconds. Okay, let's shove our numbers in. So EMF equals -n, B, leaning a bit too much to the side, B times A times, the delta of BA cos theta, all over change in time. Now, let's see, -n is fine, B is not changing, cosine of theta is not changing, but we have a change in the area. Okay, you don't really need to write this step, but it may help in structuring out and making sure that you don't mess something up in thinking, well, which part is changing? Let's identify the thing that's changing. So -n B cos theta over t, and that's going to be area final, take away area initial, and let's make our substitutions. One loop, so it's a 1 times 4 times 10 to the -3 times the cosine of 0, all over 0.1, and it's going to be multiplied by the change in A, which is 0.6, take 1.5, and we end up with a final number of 36 volts. So you can see here the change in the area really increased. No, I think there is a typo there. No, 4 millitesla. No, he's got a typo there. Let me just grab my calculator. Because he has not put the 4 times 10 to the -3 into the working of his book. Times net 1, that doesn't change. 0.6 take away 1.5 is -0.1 divided by 1, 2, 3. Yeah, so 36 times 10 to the -3. They are missing the power. Okay, or 3.6 times 10 to the -2 volts. Okay. Regardless of which, we can see here that that one is a bit bigger than the other ones that we've seen. Okay, so what we haven't done here is determine the direction at all, and that will be in our next video, because we will need to determine the direction of the current through the setup, but that requires a lot more explanation, so we will leave it until our other video. So let's have a look at our summary. In our video today, we have learnt the following. We've defined magnetic flux, and we've connected it to magnetic field strength. We've defined EMF, and we've seen how it is a product of moving a magnet, and we've calculated EMF by changing different factors. Now, for your entrance to class, please complete questions 1 to 6 in chapters 8.1 and 1 to 9 in chapter 8.2. Copy your answers into the 4.1.7 space on eLearn. Thank you very much for listening, guys. Have a great evening.